Hey, I'm Pau Sastre Miguel, a software engineer at Apple. Today, I'm going to talk about how to create immersive experiences with Metal on XROS. This year, with the launch of XROS, you will be able to create immersive experiences with familiar technologies in the Apple ecosystem. With RealityKit, you will be able to create experiences that blend your virtual content with the real world. On the other hand, if your application will take the user into a fully immersive experience, XROS also enables you to completely replace the real-world content with your own virtual content. When creating fully immersive experiences, you have a few choices when it comes to your rendering method. You can still use RealityKit, or if you prefer, you can choose Metal and ARKit APIs. Rec Room is a great example of an application that provides a fully immersive experience using compositor services to create a rendering session, Metal APIs to render frames, and ARKit to get world and hand tracking. They were able to bring support to all these technologies thanks to the Unity editor. If you'd like to write your own engine, the Compositor Services API gives you access to Metal rendering on XROS. You can combine it with ARKit, which adds world tracking and hand tracking to create a fully immersive experience. Compositor Services is the key to configure your engine to work on XROS. I'll show you how to set up the render loop, and then how to render one frame. Finally, I'll show you how to use ARKit to make your experience interactive. Start with the architecture of an XROS app. You'll get the most out of today's session if you have previous experience with Metal APIs and Metal rendering techniques. If you haven't used Metal before, check out the code samples and documentation over in developer.apple.com/metal. When you create immersive experiences on XROS with Metal, you'll start with SwiftUI to create the application and the rendering session. After creating the rendering session, you can switch to a language you might be more familiar with, like C or C++, to define the inner parts of the engine. You start by creating a type that conforms to the SwiftUI app protocol. To conform to this protocol, you will define the list of scenes in your app. On XROS, there are three main scene types. The window type provides an experience similar to 2D platforms like macOS. The volume type renders content within its bounds, and it coexists in the shared space with other applications. An immersive space allows you to render content anywhere. Whenever you render fully immersive experiences with Metal, you will choose the immersive space type. Immersive space is a new SwiftUI scene type available on XROS. It serves as the container for fully immersive experiences. To learn how to use immersive space, check out the session Go Beyond the Window with SwiftUI. When you create an immersive space scene, your application provides the content by using a type that conforms to the immersive space content protocol. Often, when creating content for an immersive space scene, applications will use RealityKit. It uses core animation and Material X under the hood. But if instead you'd like to use the power of Metal to render the content of your application, you've got another option. The Compositor Services API uses Metal and ARKit to provide immersive rendering capabilities to your application. The new Compositor Services API, introduced in XROS, provides a Metal rendering interface to be able to render the contents of an immersive space. With Compositor Services, applications can render directly into the Compositor server. It has a low IPC overhead to minimize latency, and it is built from the ground up to support both C and Swift APIs. When using Compositor Services, the immersive space content is called Compositor Layer. To create a Compositor Layer, you will need to provide two parameters. The first one is the Compositor Layer Configuration Protocol. This protocol defines the behavior and capabilities of your rendering session. The second is the Layer Renderer. This is the interface to the layer rendering session. Your application will use this object to schedule and render new frames. When writing an immersive experience with Metal, start by defining the app type. As the scene type, use immersive space. For the content type, use a compositor layer. Once the compositor layer is ready to render content, the system will call the application with the instance of the rendering session. Here is a good place to create the instance of your custom engine. and now that you have the engine instance, you can create the render thread and run the render loop by calling start. One thing to take into account when defining the scene list in your application is that by default, SwiftUI creates a Windows scene, even if the first scene in your app is an immersive space. To change that default behavior, you can modify the info plist of your app. You can add the key UI application preferred default scene session role to your application scene manifest to change the default scene type of your application. If you're using a space with a compositor space content, you will use CP scene session role immersive space application. After setting up the application and before getting in the render loop, you'll tell compositor services how to configure the layer renderer. To provide a configuration to the compositor layer, you will create a new type that conforms to the compositor layer configuration protocol. This protocol allows you to modify the setup and some of the behavior of the rendering session. The compositor layer configuration provides you two parameters. The first one is the layer capabilities. It enables you to query what features are available on device. Use the capabilities to create a valid configuration. And the second parameter is the layer renderer configuration. This type defines the configuration of your rendering session. With the configuration, you can define how your engine maps its content into the layer, enable foveated rendering, and define the color management of your pipeline. Now, I'll talk about how each of these properties will affect your engine. The first one is foveated rendering. The main goal of this feature is to allow you to render content at a higher pixel per degree density without using a bigger texture size. In a regular display pipeline, the pixels are distributed linearly in a texture. XROS optimizes this workflow by creating a map that defines what regions in the display can use a lower sampling rate. This helps reduce the power required to render your frame while maintaining the visual fidelity of the display. Using foveation whenever possible is important, as it will result in a better visual experience. A great way to visualize how foveation affects your rendering pipeline is using Xcode's Metal Debugger. With Metal Debugger, you can inspect the target textures and rasterization rate maps being used in the render pipeline. This capture shows the contents of the texture without scaling for the rasterization rate map. You can notice the different sample rates by focusing on the regions of the texture that are more compressed. With the attachment viewer options in Metal Debugger, you can scale the image to visualize the final result that the display will show. Compositor provides the foveation map using an MTL rasterization rate map for each frame. It is a good practice to always check if foveation is supported. This will change depending on the platform. For example, in the XROS simulator, foveation is not available. To enable foveation, you can set "Is foveation enabled" on the configuration. The second property is Layer Renderer Layout. This property is one of the most important configurations for your engine. It defines how each display from the headset gets mapped into the rendered content of your application. Each eye first maps into a metal texture provided by Compositor. Then, Compositor provides the index of which slice to use within that texture. And finally, Compositor provides the viewport to use within that texture slice. The Layer Renderer Layout lets you choose different mappings between the texture, slice, and viewport. With Layered, Compositor will use one texture with two slices and two viewports. With Dedicated, Compositor will use two textures with one slice and one viewport each. And finally, with Shared, Compositor will use one texture, one slice, and two different viewports for that slice. Choosing which layout to use will depend on how you set up your rendering pipeline. For example, with Layered and Shared, you will be able to perform your rendering in one single pass, so you can optimize your rendering pipeline. With Shared Layout, it might be easier to port existing codebases where foveated rendering is not an option. Layered Layout is the optimal layout, since it allows you to render your scene in a single pass while still maintaining foveated rendering. The last configuration property to discuss is color management. Compositor expects the content to be rendered with extended linear display P3 color space. XROS supports an EDR headroom of 2.0, that is 2 times the SDR range. By default, Compositor does not use a pixel format that is HDR renderable, but if your application supports HDR, you can specify RGBA16 float in the layer configuration. If you want to know more about how to render HDR with EDR, check out the session Explore HDR Rendering with EDR. To create a custom configuration in your application, start by defining a new type that conforms to the Compositor layer configuration protocol. To conform to this protocol, add the makeConfiguration method. This method provides the layer capabilities and the configuration you can modify. To enable the three properties I mentioned before, first check if foveation is supported. Then, check what layouts are supported in this device. With this information, you can set a valid layout in the configuration. In some devices, like the simulator, where the compositor only renders one view, layered won't be available. For foveation, set it to true if the device supports it. And finally, set the color format to RGBA16 float to be able to render HDR content. Returning to the code that created the compositor layer, you can now add the configuration type you just created. Now that the rendering session is configured, you can set up the render loop. You'll start by using the layer renderer object from the compositor layer. First, you'll load the resources and initialize any object that your engine will need to render frames. Then, check the state of the layer. If the layer is paused, wait until the layer is running. Once the layer is unblocked from the wait, check the layer state again. If the layer is running, you'll be able to render a frame, and once that frame is rendered, check the layer state again before rendering the next frame. If the layer state is invalidated, free the resources you created for the render loop. Now it's time to define the main function of the render loop. Until now, I've been using Swift, since the Immersive Space API is only available in Swift. But from here, I will switch to C to write the render loop. As I mentioned, the first step in the render loop is to allocate and initialize all the objects you'll need to render frames. You'll do this by calling the setup function in your custom engine. Next is the main section of the loop. The first step is to check the layer renderer state. If the state is paused, the thread will sleep until the layer renderer is running. If the layer state is running, the engine will render one frame. And finally, if the layer has been invalidated, the render loop will finish. The last step of the render loop function will be to clear any used resources. Now that the app is going through the render loop, I'll explain how to render one frame. Rendering content in XROS is always from the point of view of the device. You can use ARKit to obtain the device orientation and translation. ARKit is already available on iOS, and now XROS is introducing a whole new API which has additional features that can help you create immersive experiences. With ARKit, you can add world tracking, hand tracking, and other world sensing capabilities to your application. The new ARKit API is also built from the ground up to support C and Swift APIs, which will allow for an easier integration with existing rendering engines. To learn more about ARKit on XROS, check out Meet ARKit for spatial computing. Within the render loop, it's time to render one frame. When rendering a frame, Compositor defines two main sections. The first one is the update. Here's where you will do any work that is not input latency critical. This can be things like updating the animations you're seeing, updating your characters, or gathering inputs in your system, like hand skeleton poses. The second section of the frame is the submission section. Here's where you will perform any latency critical work. You'll also render any content that is headset pose dependent here. In order to define the timing for each of those sections, Compositor provides a timing object. This diagram defines how the timing affects the different frame sections. The CPU and GPU tracks represent the work that is being done by your application, and the Compositor track represents the work done by the Compositor server to display your frame. The timing type from Compositor services defines three main type values. First is the optimal input time. That is the best time to query the latency critical input and start rendering your frame. Second is the rendering deadline. That is the time by when your CPU and GPU work to render a frame should be finished. And third is presentation time. That is the time when your frame will be presented on display. In the two sections of your frame, the update section should happen before the optimal input time. After the update, you will wait for the optimal input time before starting the frame submission. Then you will perform the frame submission, which will submit the render work to the GPU. It is important to notice that the CPU and GPU work needs to finish before the rendering deadline. Otherwise, the compositor server won't be able to use this frame and will use a previous one instead. Finally, on the rendering deadline, the compositor server will composite this frame with the other layers in the system. Back to the render loop code. It's time to define the render new frame function. In your engine's render new frame function, you'll first query a frame from the layer renderer. With the frame object, you will be able to predict the timing information. Use that timing information to scope the update and submit intervals. Next, implement the update section. Define this section by calling the start and end update on the frame. Inside, you will gather the device inputs and update the contents of the frame. Once the update is finished, wait for the optimal input time before starting the submission. After the wait, define the submission section by calling start and end submission. Inside this section, first query the drawable object. Similar to CA Metal layer, the drawable object contains the target texture and the information that you will need to set up the render pipeline. Now that you have your drawable, you can get the final timing information that Compositor will use to render this frame. With the final timing, you can query the AR pose. It is important to set the pose in the drawable, since it will be used by the compositor to perform reprojection on the frame. Here, I'm getting the pose by calling getARPose function in my engine object. But you will need to implement the contents of this function using the ARKit wall tracking APIs. The last step of the function will be to encode all the GPU work and submit the frame. Inside the submit frame, use the drawable to render the contents of the frame as usual. Now that the render loop is rendering frames, it's time to make your immersive experience interactive. This video shows how Rec Room using Unity is already taking advantage of the ARKit and Compositor APIs to add interactivity to their application. There are two main input sources driving this interaction. ARKit's hand tracking is providing the hand skeleton to render virtual hands, and pinch events from the layer renderer are driving the user interactions. In order to make the experience interactive, you'll first gather the user input and then apply it to the contents of the scene. All this work will happen in the update section of the frame. There are two main input sources, the layer renderer and the ARKit hand tracking provider. With the layer renderer, you will get updates every time the application receives a pinch event. These updates are exposed in the form of special events. These events contain three main properties. The phase will tell you if the event is active, if it finished, or if it got cancelled. The selection ray will allow you to determine the content of the scene that had the attention when the event began. And the last event property is the manipulator pose. This is the pose of the pinch and gets updated every frame for the duration of the event. From the hand tracking API, you will be able to get the skeleton for both the left and right hands. Now it's time to add input support in the code. Before gathering the input, you will decide if your application is rendering virtual hands or if it uses pass-through hands. Add the upper limb visibility scene modifier to the immersive space to make the pass-through hands visible or hidden. To access the special events, go back to where you define the compositor layer render handler. Here, register a block in the layer renderer to get updates every time there is a new special event. If you're writing your engine code in C, you'll map the SwiftUI special event to a C type. Inside the C code, you can now receive the C event collection. One thing to keep in mind when handling the special event updates is that the updates get delivered in the main thread. This means that you will use some synchronization mechanism when reading and writing the events in your engine. Now that the events are stored in the engine, it's time to implement the gather input function. The first step is to create an object to store the current input state for this frame. This input state will store the events that you received from the layer renderer. Make sure that you are accessing your internal storage in a safe way. As for the hand skeleton, you can use the Hand Tracking Provider API from ARKit to get the latest hand anchors. And now that your application has input support, you have all the tools at your disposal to create fully immersive experiences on XROS. To recap, with SwiftUI you will define the application. With Compositor Services and Metal, you will set up the render loop and display 3D content. And finally, with ARKit, you will be able to make your experience interactive. Thank you for watching.